Welcome back to ControlX Engineering. If you're new here, my name is Akhil and I make videos about electrical engineering, control systems, and PLC programming. In the Control System Design series, we focus on electrical design and controls related topics. Today, we are diving into a fundamental yet crucial topic: load calculations. Whether you're an engineer, electrician, or just someone looking to sharpen your skills, understanding how to properly size electrical components is essential for proper operation, safety, and compliance with electrical codes. We'll break this down step by step. First, we'll go over how to calculate loads for both single phase and three phase power systems. Then, we'll talk about how to properly size disconnects, transformers, power distribution blocks, contactors, and other power components based on your total load. After that, we'll discuss how to determine the right fuse size to protect your system. And finally, we'll wrap it up with wire sizing calculations to ensure safe and efficient power distribution. By the end of this tutorial, you'll have the knowledge and confidence to size electrical components like a pro. So grab a calculator and let's get started. Every industrial control panel is built with several key electrical components that ensure safety, functionality, and power distribution. Let's break them down. Disconnect switches. These are the first line of safety, allowing you to completely isolate power from the panel when performing maintenance. But how do you size a disconnect? It has to be rated for the full load current of your system, plus any additional safety factors. Circuit breakers and fuses. These are crucial safety devices in power circuits. Their main role is to protect the circuit and connected equipment by stopping the flow of current in case of overloads or short circuits. Fuses are designed to blow or open when excessive current flows through them, breaking the circuit and preventing damage. Once blown, a fuse has to be replaced. Circuit breakers, on the other hand, are resettable devices that trip to interrupt the flow of current during fault conditions. They can be manually reset after resolving the issue. Both circuit breakers and fuses ensure the safety and longevity of electrical systems by preventing overheating and potential fires. When selecting fuses and breakers, some of the key factors to consider are circuit voltage and current ratings. Ensure that the device matches the voltage and current requirements of the circuit. Interrupting capacity. Choose one that can safely handle the maximum fault current expected. And response time. We need to select the right device based on the speed required to protect your device. Faster for sensitive equipment. Transformers. When stepping voltages up or down, transformers need to be sized based on the total VA or volt ampere demand. The designer needs to know what type of transformer is required for the application, whether it is single phase or three phase, whether the transformer will be mounted inside the control cabinet or outside, and what voltages are involved. Power distribution blocks and terminal blocks. These play an essential role in electrical circuits, particularly in managing and distributing power efficiently. Their primary purpose is to take a single power source or signal input and divide it into multiple outputs, enabling the connection of several devices or circuits to the same source. These devices help organize and distribute power efficiently, but their ampacity and voltage ratings must match or exceed the connected loads. Contactors and relays. These are used to control high power loads with a low power signal. These devices need to be rated for both voltage and current based on load calculations. How do load calculations apply? Each of these components must be sized correctly based on your total load connected, starting currents, and continuous operation factors. A miscalculation could lead to overheating or even total system failure. Now let's see how we can put this into practice with some real world examples. Consider this simple circuit. The load in this circuit is the motor M1 controlled by a VFD. We are given that a 20 HP VFD is required and the motor rated voltage is 220 volts three phase. The mains incoming power to the panel is 600 volts three phase. We will need to step this down to 220 volts using a transformer identified here as TR10. We will also need protection devices like fuses on the transformer's primary and secondary. Finally, we will need a disconnect switch to control the flow of power into the circuit. For this circuit, we will need to determine the following: transformer kVA rating required for the motor load, appropriate protection fuses, disconnect sizing, and finally the correct wire gauges required to handle the current in our circuit. Let's calculate the transformer size required for this application. Starting from the load, first let's convert the VFD power units to metric. 20 HP is approximately equal to 14.92 kilowatts. Assuming typical VFD efficiency of 90% to account for switching losses in the drive, this gives us its input power rating of 16.6 kilowatts. The apparent power measured in kVA that the transformer must supply is given by this formula. We can assume typical power factor of 0.95. and we get the required apparent power as 17.45 kVA. The closest standard rating available would be 20 kVA, so we will use that for our transformer rating. Next, we will calculate the primary and secondary protection fuses. For this, we will need to calculate the transformer full load primary and secondary currents. This is the equation for the current in a three-phase transformer. Applying this formula to the primary side, where the three-phase voltage is 600 volts, gives us 19.25 amps. According to NEC, primary fuses should be sized at 125% of the full load current. Applying this rule to the primary fuse FU10, we get 24.1 amps. Selecting the next standard size gives us 25 amps. For this application, class CC fuses could be used if the transformer's inrush current falls within the time delay capacity of the chosen fuse. Ensure the selected class CC fuse meets the necessary time delay characteristics to handle the transformer inrush current without nuisance tripping. Following similar steps, we can calculate the current on the secondary side as 65.6 amps. Selecting the next standard size gives us 70 amp fuse rating. For this application, we will go with class J fuses, which have ampere ratings up to 600 amps. They are commonly used for motor loads and transformer secondary protection. Class J fuses work effectively for this application, as they provide excellent current limiting properties and high interrupt ratings. Next, let's size the disconnect switch on the panel. We already know that it's switching 600 volts three-phase, so our disconnect must be three-pole with rated voltage of 600 volts or higher. The selected disconnect switch must have an ampere rating greater than or equal to 115% of full load current per NEC guidelines for transformers. Since we have determined that the transformer full load current, or FLA, is 19.25 amps, the adjusted current is 22.14 amps. The available standard disconnect size is 30 amps, so we will go with a three-pole 600 volt 30 amp disconnect. Other considerations for disconnect switch selection are enclosure type. Select an enclosure suitable for the environment, example NEMA 1 for indoor use or NEMA 3R for outdoor use, etc. Mounting. Ensure the switch can be mounted where needed, example wall mounted or panel mounted. SCCR rating. The disconnect switch must be rated to safely interrupt the maximum available fault current at its location in the circuit. This ensures that the switch can handle short circuit conditions without failure. Depending on the application, the switch might require lockout tagout or LOTO capabilities for safety and maintenance personnel. This is especially critical for industrial applications where personnel need assurance that the circuit is de-energized. The switch should comply with applicable industry standards such as UL or CSA certification to ensure safety and reliability. Confirm compliance with local electrical codes, example NEC or CEC. Finally, we will calculate the appropriate wire sizes to use in this circuit. For that, we will refer to the guidelines from NFPA 70 of the National Electrical Code, Table 310.16, which specifies the ampacities of both copper and aluminum conductors. Since our fuses are already rated for 125% of full load current, we will size our conductors based on the selected fuses. Looking at the table under 75-degree column, we can select 12-gauge wire for the primary side. This wire can handle up to 25 amps. Similarly, for the secondary side, I will select 4-gauge wire, which is suitable for up to 85 amps. Here's our circuit with all the wires sized as per NFPA 70. This is our completed circuit with correctly sized transformer, complete with primary and secondary protection fuses, disconnect switch, and wires sized correctly as per NFPA 70. Let's look at another example. There are two load circuits in this example. The first one is a 24-volt 20-amp power supply protected by a single-phase fuse FU20. The power supply requires single-phase 120 volts AC. The second load is a 120-volt 1500-watt heater. The heater switching is controlled by a contactor. The load is protected by a single-phase fuse FU30. The mains incoming power to this panel is 240 volts single-phase. Therefore, a single-phase step-down transformer is required to convert the 240 volts to 120 volts. We will need protection fuse on the transformer's primary. For this circuit, we need to determine the following: transformer kVA rating, appropriate protection fuses, the correct wire gauges required to handle the current in our circuit, a heater contactor, and 120 volt terminal blocks marked TB. Let's start the calculation with the transformer size required for this application. Here we have two loads: the power supply, which has an output of 480 watts at full load. Assuming an efficiency of 90%, its input power is 533 watts. The other load is the heater, and it's already known to be 1500 watts. So the total load comes out to be 2033 watts. The apparent power measured in kVA that the transformer must supply is given by this formula. We can assume typical power factor of 0.95, and we get the required apparent power as 2.14 kVA. The closest standard rating available would be 2.5 kVA, so we'll use that. Next, let's calculate the fuses required to protect our circuits. In this example, we have fuse FU10, which provides the protection to the transformer's primary side, and we have fuse FU20 and FU30, which provide the branch circuit protection. Let's calculate the transformer input fuse FU10. For single-phase circuits, we can calculate the current. For our application, the fuse is typically rated at 125% of full load current, and also depends on local standards and the type of fuse used. For a class CC time delay type, we can go with standard fuse rating of 15 amps. The transformer secondary is split into two circuits, and each circuit is protected by its own fuse. And we get 6 amps and 20 amp for the two branches. Now that we have all the currents figured out, we can size our wires. For this, we will need to refer to NEC Table 310.16, which provides the allowable ampacities for current carrying insulated conductors. Again, looking at the 75-degree column, we can see that the 14-gauge copper conductor can handle currents up to 20 amps. So we'll select this for the transformer primary branch, as well as the power supply branch. As for the heater, we can go with 12-gauge conductor, which has a rating of up to 25 amps. Here are the selected wire gauges. One thing to keep in mind is to account for voltage drops based on the length of the wires. For example, if the heater is located further away, requiring longer conductors, then maybe select larger conductors like 10 gauge or 8 gauge, depending on the length. The heater circuit requires a single-phase contactor for switching. To select the right contactor for controlling your heater, we'll need the following information. Load type. Heaters are typically resistive loads, which means they don't have inrush current associated with inductive loads like motors. We have to ensure that the contactor is rated for resistive loads. Another important factor to consider when selecting contactor is the load current that is required to be switched. In our case, we already calculated the heater current and determined it to be 12.5 amps. Ensure the selected contactor is rated for the supply voltage of our circuit, which in this case is 120 volt AC. For single-phase heater, we will typically need a single-pole contactor to switch the live circuit. If the heater was powered by two live phases, then a 2 or 3-pole contactor should be used. Since contactors use a control voltage to switch them on and off, we need to consider the correct control voltage. For most PLC-based control systems, it is common to use 24 volt as the control voltage. If the heater will be turned on and off frequently, choose a contactor designed for high switching cycles to ensure durability. So based on the criteria we just discussed, and in my application, the transformer neutral is grounded, which means a single pole contactor can be used and should have a current rating higher than 12.5 amps with a control voltage of 24 volts and rated to handle resistive loads. For this application, I've picked this electromechanical relay from Wiedmüller's D-series power relays with control voltage of 24 volt and a rated voltage of 277 volt AC. It has a continuous current rating of 30 amps, so its ratings exceed our application requirements. Lastly, we need to select suitable terminal blocks to distribute the 120 volt from the transformer to the two load circuits. The largest current it needs to carry is 12.5 amps for the heater, so any terminal block rated higher than this value will be suitable. I've selected the WDU 2.5 series feed-through terminal blocks from Wiedmüller. They have a UL current rating of 24 amps and can handle AC voltage up to 800 volts, so this is perfect for our application. Let's look at one last example. This is the single line diagram for a 480 volt three-phase circuit. We have three motors, M1, M2, and M3, with power ratings as shown. For this circuit design, we have to size the following. 3-pole fuse disconnect labeled DSC1, 3-pole contactor labeled CON1, power distribution blocks labeled PDB1, fuses FU1 to FU3, motor starters SS1 to SS3, and appropriate wires to use in this application. So let's go. Designing this circuit involves several steps to ensure compliance with NFPA and NEC standards while maintaining safety and efficiency. Here's a breakdown of the process. Let's start with the disconnect switch DSC1. To size this correctly, we need to determine the full load current that it must safely handle. The fuse disconnect is sized according to NEC 430.24, which specifies that in a group of motors, the full load current or FLC of the largest motor must be multiplied by 125%, and the FLCs of the remaining motors are summed to determine the total current. To determine the motor FLC, we will refer to NEC Table 430.250, which lists the motor FLC based on its HP for various voltage classes. From this table, we get the motor FLCs as shown here. Applying NEC 430.24 by multiplying the largest motor FLC by 125%, then summing the rest. This gives us 113 amps. Based on this calculation, I've selected this fusible 3-pole 125 amp rated disconnect from ABB's catalog and Class J 125 amp rated fuses. Next, let's size the contactor. For this, we refer to the NEC Article 430.83a, which specifies the minimum requirement for contactors used in motor circuits. Essentially, the motor contactor must be capable of making and breaking full load current of the motor and be able to withstand the starting inrush current under normal operating conditions. In addition, it must also comply with the voltage requirements of the application. So in our case, we need a three-phase contactor rated for use in 480 volts or higher voltage systems. The contactor also must meet the appropriate utilization category for the load type. For motor loads, the category is typically AC-3, which is designed for starting and stopping squirrel cage induction motors under normal operating conditions. Another consideration is that the contactor must be able to withstand short circuit conditions without damage when used in conjunction with the specified short circuit protection devices like fuses or circuit breakers. And finally, the contactor's current rating must be sufficient to handle the full load current or FLC. In our case, the contactor must be able to handle the 113 amps that we calculated earlier. Based on this, I have selected this part number from Allen Bradley, which has an operating current rating of 146 amps for 480 volt operation. Since we are connecting three motor circuits to a single contactor, we will need power distribution blocks or PDBs to split the output power safely and efficiently. NEC 314.28a and NEC 376.20b provide guidelines for selecting and installing these blocks. Some of the key selection criteria for power distribution blocks are current rating. The PDB must handle the total current required by all three motors. As per our previous calculation, the total current was 113 amps. I'll choose a PDB rated for at least 125 amps as a safety margin. If future expansion is required, I'd consider a higher rating like 150 or 175 amps rated PDB. The voltage rating must match or exceed the application voltage. Since our motors operate at 480 volts, the PDB must be rated at or above 480 volts. Standard industrial PDBs come in 600 volt AC ratings, which is suitable. The PDB must be able to accommodate all incoming and outgoing connections. In this case, the selected PDB must allow one input per phase and three outputs per phase to each motor circuit's protective device. Some PDBs require multiple input and output combinations, so choose one that fits our wiring setup. The PDB must accept the conductor sizes we are going to use in our application. Based on NEC Table 310.16, typical wire sizes for our setup might look like contactor to PDB, likely 1-aught wire, 413 amps, and from PDB to the fuses, likely 12 gauge to 6 gauge, depending on the individual motor current and wire lengths. The SCCR rating of the PDB must meet NEC 409.110, which requires power distribution blocks to have short circuit current rating or SCCR that matches the fault current level of the system. Standard industrial ratings are 10 kA, 25 kA, or 65 kA. If the system is protected by a circuit breaker or fuse, the SCCR of the PDB must be equal to or greater than the available fault current. Considering all of the above factors, I have selected the PDB 220 series from Busman, which meets all of our selection criteria. Now let's look at the fuse selection. NEC 430.52 provides rules for selecting overcurrent protective devices, OCPDs, like fuses and circuit breakers for motor branch circuits. It is important to note that fuses do not provide overload protection. This is handled separately by overload relays per NEC 430.32. Overload occurs when a motor draws more current than its full load current, or FLC, for an extended period, and this type of protection is designed to protect the motor windings from overheating due to excessive current draw over time. typically caused by mechanical overloads, example, jammed conveyor, excessive load on a pump, and so on. Typically, overload protection is provided by means of overload relays. VFDs and certain soft starters may also have built in overload protection. On the other hand, overcurrent protection is meant to protect the motor circuit wiring, not the motor, from dangerously high currents due to short circuits or ground faults. This can be achieved by using overcurrent protection devices like fuses or circuit breakers. For motor protection, time delay fuses allow for high inrush current while protecting against short circuits. Fuse rating is based on motor FLC and based on NEC Table 430.52. The fuse size can depend on the motor type and permitted percentage of FLC as per Table 430.52. Based on the table in NEC 430.52, these are the recommended fuses. Select the appropriate 3-pole fuse holders for the selected fuses. Now that we have discussed branch circuit protection using fuses, the next step is to integrate soft starters for each motor. A soft starter is a device used to gradually ramp up voltage when starting an AC motor. Instead of applying full voltage instantly, which causes high inrush current and mechanical stresses, a soft starter provides a controlled, smooth acceleration. Some of the benefits of using soft starters for motors are reduced inrush current. Instead of applying the full line voltage of 480 volts, a soft starter uses thyristors or SCRs to gradually increase the voltage to the motor. A standard across the line motor connection can cause an inrush current of up 800% of FLC. Soft starters limit the inrush current down to 150% to 300% of FLC, avoiding voltage dips that can impact other loads. Full voltage starting can cause high torque, leading to belt slippage, shaft stress, and wear and tear on the gearboxes. Soft starters allow smooth acceleration, thereby reducing or eliminating mechanical damage. Motors and mechanical components last longer with soft starting, and reduced thermal stresses on the windings means fewer insulation breakdowns. Soft starters reduce peak demand charges from utilities. By limiting the starting current, soft starters help avoid tripping breakers or blowing fuses during startup. NEC 430.32 requires that motors must be equipped with overload protection devices such as thermal overload relays or electronic overload relays. These devices disconnect the motor before critical damage occurs due to excessive current. Some soft starters include built-in overload protection and bypass contactors for improved efficiency after startup, thereby eliminating the need for separate overload protective devices. So how do we select the right soft starter for our application? Looking at the motor nameplate, we can get most of the motor rating data that we need for this assessment. Important informations that we must look for are the motor voltage and number of phases. In this case, we have 480 volt 3-phase motors. The next one is the motor power rating, which we know to be 10 HP, 25 HP, and 40 HP. And finally, we need to know the motor full load current or FLC, which we have determined using the NEC table 430.250 when we sized our disconnect switch. Select a starter that limits inrush current to 150 to 300% of FLC. Some models even allow adjustable ramp up times to fine tune the starting torque. Some soft starters include built in overload relays. If not, an external overload relay must be added. For this application, I can save space in my control cabinet by selecting a starter with built in overload protection. A built in bypass contactor improves efficiency by switching to full voltage after startup. Without a bypass, the thyristors must remain active, generating heat and wasting energy. Among control features, some soft starters allow adjustable start ramp time from 2 to 30 seconds. This is to prevent torque shock. Some also allow stop ramp time. For pump applications, choose a soft stop feature to prevent the water hammering effect. Another feature to look out for is communication protocols for the soft starter, like EtherCAT, Profinet, Ethernet IP, if you're going to be integrating the soft starter with a PLC. Then there are also environmental considerations. Some soft starters require derating at higher temperatures, for example. Another enclosure type is an important consideration. Choose NEMA ratings like 4x or 12 depending on your location. Given these considerations, this is the soft starter that I have selected. Altivar soft starter ATS480, which is suitable for controlled starting and stopping of motors for applications like pumps, fans, blowers, compressors, mixers, conveyors, and many other applications. The ADS480 family has a soft starter for every motor power rating from 2 HP to 1200 HP. This soft starter is built for demanding industrial and process environmental applications. It features advanced torque control, dynamic braking, and various protection features, including motor overload detection and protection. And lastly, let's size our wires for this project. For this, let's refer back to the NEC Table 310.16. Looking at the 75-degree insulation column, we can go with wire gauges 12, 8, and 6 for M1, M2, and M3 circuits, respectively. For the circuit to the left of the PDB, we will use the combined FLC of the three motors, which we have calculated to be 113 amps. We can go with wire gauge size 1, which can handle currents up to 150 amp continuous. That's all for today's video. If you have any questions or suggestions about today's video, please leave them in the comments below. If you found this video helpful, then please consider subscribing so you don't miss out on future tutorials. As always, thank you for watching and keep innovating.